one of the things that we see and that's not well appreciated is how energy transition is going to fragment value chains, especially traditional energy value chains, in ways that are not not well understood at this point of time, and that are difficult to also forecast. So, for example, if you take a look at where oil and gas companies are investing in energy transition, what you find is that there are big differences. A lot of them are obviously investing in renewable power, but some of them are, making big investments in CCUS and DAC, for example. Others are making investments in hydrogen, green and blue hydrogen, and so on and so forth, right? So we are seeing investments in various kinds of technologies, but most of these investments tie in very well to the asset base of these investors. So, for example, if you take Exxon's investment in Denbury, right, the acquisition of Denbury, right, it is because it aligns very well with their plans and goals and aspirations for the low carbon solutions business. So, we are kind of seeing these touch points where people are trying to see where an investment would make a lot of sense with their existing asset base. But what that does is it fragments the value chain, right? So traditionally, what would have been an investment focused exclusively on EOR, for example, now is serving other markets. So managing this complexity, so complexity is going to increase, and managing this complexity is going to become challenging. You kind of see similar things in the acquisitions of early stage companies, for example. Oil and gas companies actually have been very prolific in acquiring a lot of early stage companies, and we are showing some of them here. Again, like if you try to draw patterns to say like, okay, where is there a strong fit? It is hard to make those. But when you look at each of the individual companies and where they are and what their asset base looks like, then some of these acquisitions make a lot of sense. We also think that some of the speed and volume of deals that we have seen by large oil and gas companies in and around energy transition should slow here going forward. One of the areas where we have been doing a lot of work, some of this work we have actually done with ARPA-E over the last 5-6 years, but then also with the refining independence, is how will the refining infrastructure change? The world has over 600 refineries. The refining infrastructure doesn't quite enjoy the same kind of appeal that the electricity grid enjoys, but it is no less important because these refineries are processing 100 million barrels of oil every day and delivering those refined products all around the world. And a lot of these refineries have been configured, optimized over decades to produce fuels at the lowest cost possible. But as energy transition advances, as the penetration of EVs increases, the need for fuels will decrease. So we're going to see some of the smaller refineries, some of the simpler refineries drop off the curve, but it will get to a point where even well-integrated refineries will struggle because there's not enough fuel demand. How are those refineries going to change? How are those refineries going to prepare for this transition? I think this is a space that doesn't get the kind of attention that, for example, the challenges associated with the grid usually gets. And so we've been trying to draw some attention to this. And what we are showing here on the left is we are showing how product distribution or product yields, if you will, at a high level out of the refining infrastructure is today in 2025, how that could change by 2035 based on lower fuel demand. And you'll see that the stacks associated with fuels are declining while the stacks associated with other products are going up. But what is interesting is that the asphalt production stack really increases there. But then eventually, right, by 2050, we'll get to utopia where all these refineries are going to be reconfigured to make chemicals and petrochemicals. Obviously, it's easy for us to do that on a PowerPoint. It's very hard to do that in the actual refineries. On the right, what we are trying to do is forecast margins. And what we see is actually margins in 2050 will look really nice, better than what margins today exist. But you have to survive through 2050, and that's the challenge, because the margins in the next 15, 20 years, as you go through this transition, are going to look horrendous. And how is the refining industry going to address that is going to be a challenge. The refining industry is already under a lot of stress and duress. So yesterday, if you didn't quite see it, but we have had activist investors take very aggressive positions in a few of the large refineries. Yesterday, one of the activist investors issued a pretty nasty letter to one of these large refining independents. It makes incredible reading, and it kind of shows you some of the challenges that refining is going to face in the next 10, 15, 20 years. Again, it's easy for people to take pot shots at refiners, but transforming these businesses is going to be incredibly hard. I spent a couple of years in refining operations in ConocoPhillips in the early part of my career, and these are very, very tough, complex pieces of infrastructure that cannot be changed easily. E-fuels gets, and here now we are building the case for Greenwells here, Jim, but e-fuels is getting a lot of attention, but the cost of e-fuels is very high, and the bulk of that cost is electricity cost, right? So the traditional approach of we're going to build massive plants for e-fuels and try to leverage economies of scale, that's one approach, and we'll kind of see how those experiments evolve. But an alternative approach could be Greenwells or some of the ideas that you have in...
You're still too much. You got to go down to the 25 is on my... Anyway.
So we'll let you talk about that, Jim,
okay.
Right?
Sorry to interrupt.
No, I know it's still high, but it would be interesting to see, if you take more of a distributed scale approach, what does that look like? And we'll talk about that a little bit more. A lot of these problems could go away if small modular nuclear reactors, or broadly speaking, nuclear is successful, if we as a society can get comfortable around permitting nuclear capacity. But there's a lot of very interesting innovation that's happening in this space. And right now, a lot of this is focused on rapidly growing demand segments like data centers, for example. So with that, let's get into the conversation today. Jim, we'll start with you. Tell us about Greenwells. Tell us what you've been up to at ARPA. You've been at ARPA-E for a little over 2 years.
Yeah, 2 years. So I want to back up on so ARPA-E, we're part of the Department of Energy. We're very different than the rest of the Department of Energy. The program directors, by title, we set up the programs, and we're all on 3-year contracts. So at the end of this year, my contract's up. And, other people come in, and the idea is to get that flow of ideas, hopefully from industry. We've had very few oil people. I think maybe I was the only one that's gone through ARPA-E. And for one thing, right away, it doesn't really pay like oil and gas. I can tell you that right up front. And it's a lot of more work and travel than you could ever imagine. Just talk to my wife. So, but that being said, it's a really great organization because there's now 20 of us PDs, so we all have different programs. And we have small modular reactor program, had that for years. So I can talk to nuclear physicists. We also have a fusion program. So I've actually reviewed a lot of the proposals in the nuclear fission and atomic reactors. We have some programs there on how to make that cheaper, right? But it's very far off. But then I understand, and I've looked at some of the companies you already showed here. Some of these are ARPA-E companies, and the purpose of ARPA-E is to commercialize technology, which means we need to find the right problem to solve. That's what we are. We do not have a roadmap. We are technology agnostic. We want to solve the problem. And so we're looking for problems to solve. So one of the problems I came in with, e-fuels, I said, how do we make fuels, hydrocarbon fuels, compatible with infrastructure and end-use devices, because that kind of made sense to me. And then on the front end, it's like, well, they're just too expensive. Well, I did some digging and a lot of research to figure out, okay, this is how we can get it close to par with what today's hydrocarbon fuels are. Definitely where you would have no credits and still be able to run our economies like we're used to running today. Maybe slightly more expensive, but definitely would not crater the economy. So in Greenwells, I target basically $4 a gallon with no incentives. If you include the incentives in there, it goes to zero with today's incentives. But you got to think longer term. So that was one of the key objectives around Greenwells, or really any of our programs that we set out, is in ARPA-E, because they are reviewed internally, and also all the proposals are reviewed externally. So it goes through extensive review processes, and honestly, the toughest ones are all the different PDs within ARPA-E that we internally really hammer on each other in a nice way to make a better program, asking a lot of questions, because you have both academics and people from different industries. For example, Jack Leonard just went off, and he came out of kind of the oil and gas industry from air products type side of the business, and a great chemical engineer, set up some programs on basically taking our infrastructure on pipelines and how do we repair them in situ, and came up with companies there. So now there's some startup companies in that space that are getting some funding and understanding how we can repair our infrastructure in the cheapest way possible. So that's, I think, a great one. Jack, he reviewed my program and said, you want to do Greenwells, you want to do reactors that basically follow load of renewables. They're intimate. He goes, Jim, those are chemical reactors. You can't do that. Reactors you have to run steady state. They're going to take your chemical engineering degree away from you. I go, I don't have to worry about that. I'm a mechanical engineer. So that was but we had a good time, like I said. So setting up the Greenwells program, the other objective around that is cost. And seriously, I was looking at $25 on the cost piece as the maximum. And that's realistic if you don't have the grid. So you have to go behind the grid, you go out in the middle of nowhere, and guess what? That happens to be in the United States where your highest capacity factors are. In the US is basically right down the center of the US, of course, West Texas, because it always has the resources, right? And then you just head all the way up to North Dakota, kind of head over into Iowa, even over to Illinois, and that's where you get a large amount of renewables. This is all mapped, by the way, by NREL. They've mapped the entire United States on 11 square mile grids with an 8-year weather history for both wind and solar. So you can get a pretty good idea of where you're gonna have high capacity factors in the United States. And they overlaid that on the cost of electrolysis, so you know where I can get my $2 hydrogen. So I kind of added that up. I go, all right, so if this really works and we can get it to work and make these liquids with all these great performers and discover new pathways to make these liquids, can I get the capacity? Can I make enough of it? So I just today looked at the current data, and yeah, sure enough, if I took all the hydrogen that can make it $2 a kilogram, it equated to 15 million barrels a day. And they expect that number to increase. So yeah, we do have the capacity for renewables. We do have actually the economics behind it if you go, again, behind the grid, but you're talking terawatts if you build all this out remotely. And then you're talking about reactor systems that basically can run remotely following the loads of whatever the renewables would provide.
Yeah.
So anyway, I'll stop there.
No, that's helpful, Jim. Good introduction. So I'm at $4 a gallon. You are a Greenwells awardee, and where are we? So again, to a certain extent, right? Jim also does a lot of conceptualizing on PowerPoint, maybe not PowerPoint, maybe Word documents. So, but at the end of the day, it's you trying to translate that into reality in the lab. So tell us a little bit about your technology.
So we're really pleased to be a part of the program. It follows on a long history at our parent company, Nexeris, and then where we're working in the HeatPath Solutions part on really looking at innovative ways to improve heat transfer, catalytic reactor materials, and things like that. So, I am also not in jeopardy of having my chemical engineering degree taken away because my PhD is in material science. So I've done a lot in engineering the material sets, the coating technologies, a lot of the nuts and bolts of how we would put these reactors together in a new and different way. And I'm very fortunate to be working with a great team on this so that we're looking at how to build an innovative design in which we have interlayered membrane reactor and microchannel reactors. And the stack will run in a way that we end up getting about 90% completion of the reaction on a single pass, as opposed to being limited the way a methanol production would be now. So the way we're going at this is by keeping the reactor size small and highly efficient, eliminating those recycle loops, things like that.
Mm-hmm. And what do you see, like what are the key bottlenecks right now, or the key pain points for the technology? Right? What do you need to address?
Right. So what we're following right now is a plan in which, we're de-risking different aspects of the technology. They've been proven to a certain point, and then we have developed, based on sound principles of how microreactor channels, or how microreactors in general work, tying together those models with permeance values for the membranes that have been taken, so we're kind of bringing everything together. The project's great in that regard. It allows us to bring together expertise that has kind of been stuff we've known about and not had a vehicle to really pull together. So I've spent time out, raising funds for technology over the past year, and this, has been such a great program for us because I can also, bring together some of the tools I've learned about how to get to inflection points and minimally viable products. So we're driving very hard, and in contrast to a program that might, seem leisurely in pace in other aspects of my career, this one is very much, we're going to get a minimally viable product done, get that demonstrated, and I have a very helpful guy at my shoulder to help me remember that that's the goal. So, and that's what we're doing. It's awesome.
So Jim, tell us a little bit about what are some of the other technologies that are being tried under Greenwells?
Sure, we have 14 teams, 14 different technologies. 6 of them are thermochemical, for example, like what Matt is talking about here. 6 of them are electrochemical. And then we have 1 that is biological, because I want a biological one. And then there's 1 doing plasma catalysis, which is a very new process that kind of just started in the States, but it's been going on in Europe for several years. And we think we should know a lot more about plasma catalysis. Definitely AI will help a lot with plasma catalysis because truly nobody really knows what's going on. And it's very counterintuitive. We're getting some results from it, and it's driving us crazy already, and it's just started.
So in the thermochemical pathways, what are some, can you give us a couple of technologies in a little bit more depth?
Well, you can read online. The problem is, all right, as a program manager, I know all the details, and I have an NDA, of course, with each one. And they're groups, so they're typically the team is a very important aspect in our Greenwells program. And then once a year we have the annual meeting. Everybody gets together. Plus, I invite other people and VCs to come and ask questions. But you want them to interact because it's really a hard, challenging. We have metrics around 50%. Energy efficiency, meaning 50% of the electron energy has to end up into the liquid, right? That's part of the goal. And the reason I set such a difficult goal, it's theoretically, it is possible, but it's on the verge of being close to impossible. But the purpose is for me, for example, reverse water gas shift and Fischer-Tropsch is pretty well known, but it's never going to work in this environment. And honestly, I really had no interest in that pathway because it's more developed. For example, ARPA-E, we're looking at new pathways. We want to see if we can break through with another way to make these hydrocarbons. So that's really the
Are
drive.
most of the pathways, let me ask it as a question, right? Like, what are they making the pathways? So methanol, for example, is
Right.
one. What are some of the other
So
liquids they are trying?
So again, we're hydrogenating CO2 and hydrogen together, right, to make
Yeah.
this liquid. And so you can make it into methanol. People actually have done that. There's a plant in Iceland doing that. But to actually do that and run it in a transient mode, again, the transient mode behind the meter, I can get the $25. I can get less than $25. And then you can set it up into a project, right? Like a 100 megawatt facility or something like wind or solar, right? So if you look at it from a project perspective, $200 million project, you can start producing 350 barrels a day, and there's your business, right? And then who's going to do that? Which is why I asked Charles earlier, right?
Yeah.
Who actually integrates all of that together, right? And today, no one does. So that's a big part of it. And the other thing, it could be methanol. It could be, the other one is ethanol is a popular one. They're going to make liquids. One of them is propane, and then SAF, or fast SAF feedstock, which is the most difficult, obviously.
Yeah.
And so the ones on Seaba, they're typically thermochemical. When you do thermochemical, there's basically two routes, right? It's sort of kind of a reverse water gas shift, or you go over into methanol, to olefins type work. But people know if you just do methanol to olefins, you're going to need another reactor to go to the heavier hydrocarbons, and that just adds cost, and we can't afford that. So we really are looking for something unique, and we have some really good teams in there. So the other teams, making methanol, that's fine. Making SAF is another one that like Cestion is doing, for example, and one of their partners is Total, and also University of Purdue looking at oligomerization. So I mean, it's a pretty interesting, great group of folks. All the teams are great. I mean, Matt's not working by himself either. He has a very strong
That's great.
background with it too.
Yeah, it's the
So Matt, I mean, can your technology make other stuff, or do you think methanol is the most is the most likely product?
right. Well, I think that there are options, beyond what we're looking at here, but and we're working on that. As I mentioned earlier, the program has a lot of support for us to go out and talk with folks and really learn both where our technology we're working on goes, but it also gives you a lot of credibility to, sit down with somebody and say, tell me what here's the technology we're working on, here's where we're going, help me understand the gaps that you see or the gaps that you have. And so we look at the reactor design and the materials and technologies we're proving to be, platforms that we, will explore in multiple avenues. That's what we do as a business in other areas.
So microreactors, I guess, what's the track record been around microreactors from a commercial point of view?
Yeah, I think that there are definitely aspects of it that have been out there and evaluated at different scales. I'm in Columbus, so I know the folks at Velocys pretty well, and we have seen how they have been able to take things to a certain place, particularly for this. When you start to look at dynamic reactors, and the intention of bringing reactors up to speed or up to temperature, I should say, and then cooling them back down. A lot of the strengths of those designs become challenges you accept, and to hit some of the gradients that one expects from the grid, or not from the grid, but from an intermittent power supply. So that's kind of the trade-off that we have made. We do have part of our team has a lot of expertise in that space. So we're able to hit the design part of it very hard at the beginning and get these minimally viable prototypes up in a matter of months instead of years. So we'll be getting that running very soon.
So, Jim, electrochemical pathways.
Yes.
I'm not exactly optimistic about electrochemical pathways.
Well, I know you're not. I mean, I don't know, but I mean, most people. I'd be surprised if anybody
A
here in the
lot of-
audience
Yeah.
would go, "Oh yeah, Jim, electrochemical, please stop." You know, I mean, what do we have? Maybe 2 commercial processes that are electrochemical today. Yeah,
Those are 2 more than I know, but that's okay.
Oh, come on. Where do you think all that aluminum comes from? That's anyway, let's not talk about aluminum. But what we have is I totally understand why you'd have hesitancy there. And first of all, electrochemistry is very sensitive to inputs that aren't like barely pure, right? And so oil and gas, the last thing you get is purity on the feedstock. You get all sorts of cats and dogs in that mess, right? And that's what the oil industry does. It's experts at separating it at massive scale and making their liquids, right? Okay. But for electrochemistry, we're talking about CO2 and hydrogen. There's not a lot of cats and dogs in there. So you take advantage of that. And they have developed certain chemistry or certain professors / small companies have come up with really interesting electrochemical reactors, like they call it, where you add the water in with the CO2, an electrochemical reactor, and out comes the hydrocarbons. Right away. Oh, I have my C2s. Oh, I have C3s. Actually, the propane one, he's already proven on a
This is
on a
similar
cell.
to like Virent's technology, or
No, I mean, this one's coming out of IIT.
okay.
It's very recent. The Virent, yeah, they've done some. Virent was doing liquid phase work where they're, but
Yeah, we've part of what we do is at HeatPath we work with a lot of different folks to help in that space where people are developing new technologies, new kind of applications, and we're working with some folks that are making some really interesting products electrochemically, and then it becomes more of a how do you build up longer chain molecules or do things with them. So.
yeah. But it's a huge challenge to do that at 50% efficiency. That means and for electrochemistry, your Faraday efficiency has to be over 90%. Typically, they have pretty good selectivity. You have to have at least 100 milliamps per centimeter squared on your cell, let alone putting that into a stack system. It's hard. Yeah, they call it ARPA-E hard. I mean, it's going to be very challenging. And they don't have long. I mean, after 3 years, I want this thing running and making liquids. That means after 2 years, they have to have that thing set up and proving to me that it's going to start to run.
Yeah.
Otherwise, we pull the funding and go,
No, I mean, I think ARPA is definitely the agency that should be funding electrochemical pathways, right? I mean, anything that people are skeptical about should be the kind of stuff that ARPA should be funding conceptually. And that's what the design of the agency was.
Yeah.
So, I was just curious, right? Like where some of that technology stands. A couple of years ago, we had a fellow from one of the large chemical companies come who was an electrochemical expert, and they had spent 5-6 years looking at electrochemical pathways in chemicals, and eventually they walked away from a lot of that. But so Matt, a lot of it is in early stages, but commercially, or like if you were to paint a picture of what your aspiration would be to commercialize the technology, what would that look like, right? Like, if you were to say, advance this in the lab further, what's the next step for you?
Yeah, I think that for us, getting to kind of the minimally viable product and then getting that up to, the scale of demonstration we have on the program is about 2 liters per day. Okay. And that's on a highly variable 3-day cycle of what the actual solar and wind combined kind of renewable profile looks like. I think, once we get there, we'll have that, demonstration unit. And in some of our, conversations getting ready for having this conversation, you ask me, what the big hurdles are for a company like us to get to that next stage. And, one of the biggest hurdles is how do we get the initial minimally viable product done, even in a, even at that scale, molecules are pretty capital intensive, and you've got to have, this is not garage work, and so that's like hurdle one. And then getting there, then understanding how do we, as technical experts in our space, interface with folks who are used to dealing with larger and larger scales of how these sort of operations go. Not all the material science in the world is not going to save me from having to say, all right, I need other people to help me get this to the next stage. And we're very open to
so
that.
what kinds of help does that look like? Would you need to partner with somebody, let's say, who can build microreactors? Would you need to partner? What does?
Yeah, I mean, I think what we're going to do, we'll have, our team has a lot of expertise in doing kind of those, demonstrator, highly engineered, highly instrumented sort of things. And then as we begin to move that from that sort of prototype toward, something that's more manufacturable and scalable for demonstration, we'll definitely be looking for folks who have experience in how integrated systems work. We're looking at, a highly dynamic system with some assumptions about what feeds into it and what's on the other end of that. Mm-hmm. And ultimately finding our place in an ecosystem, sort of what was talked about earlier today with, having a set of folks that have a common vision, that will be necessary.
Okay. Does ARPA-E help with that? Do you guys help with finding partners, bringing them together?
That's one of my jobs, is like a matchmaker. I don't tell them what to do ever. I said, well, I can recommend or make suggestions on either industry or other partners. There's a lot of really, we have a really good set of industry folks that, work with us or are interested in some of these projects. And, will, as things progress, they will come in, maybe help, or, it's again, all up to them on what they want to do. But again, the idea is that viable commercial product that we focus on. And they have the 3 years to get that done. And then after that, maybe then we can do a scale up. We already have places located for doing scale up and actually put this out in the field and testing it in a more live scenario.
What are these places? How do they, so you're partnering with some?
Yeah, different. For example, NRELS has the flat irons, and they have solar now and wind, and they're putting in a DC grid and things to be able to do it there. But
some sort of a standardized test facility where you
standardized. And there's some other private area companies that are doing a similar thing for this type of work. But I think the concept is again, if we're successful, we're not just going to sit there. Wow, now what? No, we already have a plan.
Yeah.
So by then 2030, we can get it up to a viable prototype. So then the next scale up would be more of a demo type facility for commercialization of whatever we're making, methanol or ethanol or jet fuel or all three.
I'm sure there are lots of technologies that are being developed outside of the Greenwells awardees in this space, right? That you probably got a lot of applications, and you probably had to pick a few, right? Mm-hmm. Does ARPA-E track what's happening to some of the more promising ones, the ones that were on the bubble that didn't quite get through?
Some of them I didn't like because of the intermittency problem that we have, or the intermittency part of our problem. There are some really good steady state ones that I liked. And fortunately, DARPA has launched a FOA like a few months after me on taking tail gas and making that into liquid fuel. All right, so
tail gas out of
exhaust.
Oh, really? Okay.
Yeah, and so of course I know the program director, and I had 98 concept papers, but I down selected to like 44. So of those other concept papers, like 25 of them or all of them, I said, hey, go look at this over here. And so then it went over to the other person that I thought, and then we talked about, he asked some questions. So that way it worked out fairly well for DARPA, because obviously, if you can make synthetic e-fuels, the value proposition for the military is much different than what I do. they may have a steady state system running off a nuclear reactor, let's say, for example. It's not far-fetched. Yeah.
You said that a lot of companies and institutions reach out to ARPA-E. Where are you seeing interest in industry for Greenwells? You don't have to name the companies, but is it coming from oil and gas majors? Is it coming from technology licenses? Where are you, if you're seeing some interest?
So yeah, we definitely see a lot of interest. I see it more on the automotive supplier side.
Really? Okay.
And you kind of look at this problem, you're going, oh, automotive supplier. Well, yeah, you're talking about wanting to make these reactor systems, like I said, 100 megawatt, renewables, again, a very distributed energy play, right? And 100 megawatts makes about 350 barrels a day, which is considerably extremely small on an oil and gas standard. But if you want to make 100,000 barrels a day, I need 30 megawatts or 30 gigawatts. I'm not going to get 30 gigawatts of renewable. That doesn't make any sense, right? So to do it distributedly, that means I have to make thousands of these reactors.
Yeah.
That's mass production. Oil and gas doesn't do mass production, right? But automotive, they look at that, So yeah, that's a.
Okay, so that's why the components, so tier one component suppliers into the automotive industry, that's the interest. So broadly, conceptually, you could say a lot of industrial manufacturing companies should also be interested.
Yes, and they are, and and another story is where all these microreactors start, and they actually started back that I know of in the mid '90s, when I was at Honda, and then I was the large project leader for onboard fuel reforming. And I was looking at onboard fuel, liquid fuels like gasoline. Actually, gasoline, Exxon, Toyota made an awesome onboard gasoline reformer. Fabulous job, back in the night. You guys, I'm sure, can find the papers on it. And yeah, it was incredible. And plugged it into a fuel cell, ran on a vehicle, right? And then I worked on one in Honda, and looking at either kerosene or something similar. But the point is that these were microreactors, and we were looking at microreactors. It was before Velocis ever started, and we were doing, basically space velocities. Well, but technically we were doing orders of magnitude more than what oil and gas would ever see, right? But of course, we're in the automotive there, and they were very, okay, this is interesting. They know how to do coatings. They know how to mass produce. They know how to, make things cheaply. So, DOE kind of supported that onboard reforming until about 2002. And then when Seaba came on to run EREs, they said, no, we're not going to worry about that. We're just going to have hydrogen on board. And after that, all that type of work stopped, and all that infrastructure support that they had, like there are companies doing really fast testing of all new catalysts and everything, because once you really reduce the mass transport limitations on catalysis, now the materials act very, very different. And so what are you going to use? How are you going to do this? So all that work was done in the late 90s, but then all of it went away when there was no more funding. And now we're kind of bringing it back.
So, Matt, this will be a difficult question, but Velocis that whole idea has been around for a long period of time, but commercial application has still been elusive, right? No, this is not a criticism of Velocis. It's a tough problem, it's a tough challenge, right?
Yep.
Also, the application that they picked, gas to liquids, is challenging, right? For various reasons.
Yeah.
So do you think that it's because of the technology and the microreactor approach, or do you think it's more we just haven't found the right application for microreactors?
Well, I would say you kind of, from my perspective, again, just looking at it, the process that you're looking at for an FT microreactor is really challenging. I mean, we tinker in, I do some stuff in FT and in a fixed bed sort of reactor space, and that is, that's a very complicated product coming off of that. So that is, I would say, another layer of complexity than we're taking on here with a much simpler molecule,
Mhm.
shorter molecule, and all of that. Also building in the membrane component. I think that these are things that we're using a lot of knowledge and things that were learned, and we're applying it to a different use case. So
Yeah. So this is just one of the technologies that HeatPath has.
Yep.
Can you tell us a little bit more about some of the other technologies in your portfolio?
Yeah, we have been at this for a while. I would say, within Nexceris, I've been working on catalysis problems for a little over a decade, different sorts of things.
Mhm.
I think my most colorful story is that I was working on ethanol abatement, and I'm one of the few people I think that's ever been on the roof of a White Castle bakery and looking at how do we help bakeries solve their emissions issues, and did that. So but a lot of different things, and what we really found was a place where we had recurring interest and ways of working with people who were being willing to take on technical risk and having materials knowledge to really start combining systems in ways that were not the status quo. So we have a lot of technologies that work in what have become kind of the high complex and high heat transfer style of reactors, where people are generally trying to intensify what they're doing. So we've developed a lot of process technologies around that. So we're very active in both developing, some catalyst materials when what's available isn't working, and we've become very adept at working with, other people's catalysts that have been purchased, and we help package them and turn that around. So, that led us to our namesake product anyway, our HeatPath platform.
Mhm.
And that's a technology I developed in collaboration with a catalyst company, looking at heat exchange and how to improve energy efficiencies in steam methane reforming. So we offer we offer that kind of platform. We call it a carrier because when I talk about catalyst supports, I inevitably end up kind of having a different conversation. But this is like a core of high heat transfer material that we can use to manage heat in those fixed bed reactors. So we work on that for a range of different chemical reactions. We're, again, catalyst agnostic a lot of the time. If folks want to use technologies we have and they have a catalyst they like, okay, great, let's work on that together. And so this type of program where we're pulling together different people's technologies and materials background, design experience, thing like that, that's really in our wheelhouse as an organization, and we can work with collaboration is just a big part of how we reach the market with our products.
Okay, let's open this up to questions from the audience.
Thank you for the interesting panel. So I have a question on when ARPA-E thinks about new technology, how does it think about whether existing infrastructure is going to be relevant, or is it a technology that is completely new, which is going to need a completely different sort of infrastructure?
That's a case-by-case basis, and it's also heavily dependent upon who the PDs are coming into the organization, for one thing. For example, we just, one of the newer PDs are coming in, and she's a professor but has a big upstream oil background around fracking, and she's looking at new concepts around fracking, but yet doing it in a more environmentally sound way, for example. So, when we look at, and it depends on whomever else you talk to. One about battery recycling. We have the one around AI and applying that toward catalytic discovery. And we even have quantum computing, where we're looking at what problem and how best to, what's the right way, where the architecture is with respect to quantum computing, and then how ARPA-E could expand that or help move that forward in a more effective way. So it's, like I said, it's all been very broad, and I've already mentioned the fusion and the fission, small modular reactors, and the heat, and we do clean steel. So basically, it's a very broad portfolio. When you look, I think we're started in 2008, and it takes a little time to build up, but since 2008, then I think we've launched something like about over 100 companies, startup companies, and right now several of them, if you count them all up that we know of, because there's no official way to track it, it's like a couple $100 billion in capital. So it's been a really good investment in that respect, that we've been really fortunate to tap some technology areas that have proven out to be very effective. And another one, ESP, I don't know why they have such difficult names today, but SPQ is a clean water company that's now sitting over in Halliburton Labs, and it's designed to basically take frac water or any type of wastewater and clean it up at a very low cost. It's very well heat integrated, and it makes very clean water that you can actually use to irrigate crops with, for example, and do it for less than whatever, like $75 or 75 cents a barrel for your cleanup cost. So again, you hit the targets that the customer wants. Something about, you have the dog food. Well, the dogs are coming, and that's a really good thing. And they're already prototyping it out in the Permian as we speak. And that was definitely spun out of ARPA-E, where I funded the guys. And I got my boiling background because I also did 4 years in Calgary, and I did the oil sands production for SAGD. So pros and cons, great process, but a $10 billion mega project is a kind of a beast, and a lot of other issues, nothing to do with technology, honestly, but very helpful to understand project economics and what things happen, which is why I brought that skill set back into ARPA-E, and I'm looking at Greenwells from a project perspective and project economics.
So we are at time, but Jim and Matt can maybe hang out for a little bit more. But so we'll call this to a close here today. But we have one more day, so join us tomorrow for Chemicals Day, and we have an equally exciting lineup of speakers tomorrow. So we'll see you tomorrow, and thank you. And let's give the speakers a hand here.
Thanks, Uday.
Thank you.